Okay, we're going to begin the topic of electric charge. So we're going to start looking at protons, electrons, how things can be charged. We're going to talk about the basic properties. We're going to differentiate between conductors and insulators. And then we're going to talk about charging by three methods: contact, induction, and polarization. Okay, this topic is purely conceptual. There's really almost no, I shouldn't say no, but there's almost no mathematical part to this topic. It's definitely not going to be a part 3 on your test. All right? And your test in general, and we'll go over this tomorrow, a lot of this test is conceptual. The only mathematical stuff we really went into was some of the stuff with like the speed of light and like EM waves and the frequencies and stuff, and then stuff with like Snell's law and the critical angle. So the math part of this test is really pretty simple. So in the past, like last year, I remember the class last year did really well on this test. Okay, so I'm hoping to keep up the trend that we can do well in this, because the first test of the quarter, students did well in general. The average was in like the high 80s. So I'm hoping that this next test will be around the same so that people's grades are pretty good this quarter. Yeah. Don't know. That's what I'm trying to figure out still. I got to make it up still. So until I make it up, I won't know. I'll make it up today. I'm actually going to be on the train for a few hours today, so I'm going to be writing the test when I'm doing that. I'm heading out to visit my family. My brother's wife's had a baby. So I'm going to visit today, and then I'm going to come back tonight. Mike? Three every quarter, yeah. Even the fourth quarter is going to be 3 tests. The fourth quarter, though, you only have 2 problem sets. So the last test of the year, I don't give you a problem set for. It's like a little treat / grading everything in like a day for problem sets would be insane. So it's a treat for you and me at the same time. All right, so let's talk about electric charge. First, the common misconception for electric charge is that either you can gain electrons or gain protons. You can't gain protons. Let's start by making sure we understand that. Why can't protons be moved? Where are they located? In the nucleus. Where are electrons located? Somewhere around the nucleus, outside. Now, I'm not going to go into like shells and valence electrons, because theory has changed so much now that quantum physics is really around. So we've really kind of aborted the whole idea of shells and rings, and it's more of like where are they located probability-wise now with quantum mechanics. So not even going to go into any of that, but the idea behind it is that electrons are the things that move. Electrons move. So if an object is negatively charged, it has more electrons than protons, or it has gained electrons. If an object is positively charged, it has lost electrons. It doesn't gain protons, but it loses electrons. And think about it. Imagine you have a neutral object. A neutral object might be something where, let's hypothetically look and say that an object has 4 electrons and 4 protons. Okay, so we're looking at 4 hydrogen atoms together, all near one another. Oh, not hydrogen. Hydrogen would be just a proton, right? Does hydrogen have an electron? Sure. Everybody remember from chemistry? Yeah. Does it? Yeah, it does have an electron? I was thinking it was just a proton for some reason. It's 1 and 1? Okay. So we're looking at 4 electrons, 4 protons. I'm not sure. It might be just a proton.
Don't they have the same number of protons as electrons?
For some reason, I remembered hydrogen only being just a single proton. Maybe that's a positron. I'm forgetting which one. Either way. So we've got 4 electrons, 4 protons, or a neutral charge in general. So if this object were somehow only a positive charge, or somehow it were net positive, it would mean that you would lose electrons.
1 proton, 0 neutrons.
1 proton, 0 neutrons, yes, but is there also an electron?
Not saying it.
There's an electron.
There is. Okay, thank you. Then it's the neutrons that were 0 I was thinking of. It's okay. So, take a look now. If we have 2 fewer electrons, this has a net positive 2 charge. It's pretty common sense to look at this to see there are 4 positive charges, 2 negative charges, so 2 and 2 balance, leaving behind 2 positive charges. So this would be a positive 2 charge as like a net charge. Again, these would kind of cancel. These would kind of cancel, leaving behind 2 overall positive charges. So remember that you can only lose or gain electrons. You can only lose or gain electrons. You can't gain protons. Let's see what else. Now, we talked about certain substances that are naturally charged. For example, hair products have a natural charge on them. So anything that's coming out like an aerosol can usually is charged on it. So if you've ever sprayed hairspray, why does it cling to your hair? It's made to cling to your hair. So it doesn't get all over like your forehead and stuff when you spray hairspray, all that like grossness. So when you're spraying it, it's actually made to actually grip onto your hair. Because your hair is certainly charged one way or the other. Now, have you ever taken like a comb and brushed it through your hair? Probably guys, girls use like hair brushes, right? They don't use combs. So if you take like a comb and brush it through your hair, ever look at the comb and you see like hair on it afterward, and the hair is kind of clinging to the comb? You have to kind of like get it off the comb. It's kind of gross, but it sticks to it. That's because when you're brushing your hair, you're charging your hair one way, and you're charging the comb the other way. So the electrons are jumping off of your hair onto the comb surface, making the hair that's left on there positively charged and the comb negatively charged, which is why the hair kind of sticks to it. It's the same thing as a balloon. If you rub a balloon against your hair, and then you go to pull the balloon away, what happens to your hair? It kind of does this, right? Like pulls toward the balloon. The reason it pulls toward the balloon is because when you're rubbing the balloon against your hair, you're displacing some of those electrons. Some of them are moving between your hair and the balloon. So one of the two objects gets charged. Now, if the balloon gains electrons, let's draw a diagram of this. So let's say you have a balloon and a person. It's a big balloon, actually. Whatever. So say they rub it against their hair vigorously several times, causing the balloon to get a net positive charge. How is that possible? What would have had to happen for the balloon to get a net positive charge? How could you get a positive charge? It has to do what? Well, what gains? The hair gains electrons and the balloon loses electrons. So this is what, so if I draw hair on this person, okay, the electrons are literally moving from the balloon to the hair. So the person's hair now has a net negative charge on the person's hair. So as a result, the charges are opposites. When you try to remove the balloon, what do you know about opposites? Opposites attract. So as a result, when you move the balloon away, the hair gets attracted toward the balloon. Because that's physically what's happening here. Okay? The hair gets pulled toward the actual balloon because of the charges that change. Now, what about the fact that what happens if charges are the same? Instead of opposite. Yeah, very good. The word repel, they move away or they push away from one another. All right, they push away from each other. You can never create nor destroy charge. It's always conserved. It's a matter of where it comes from. So if something loses electrons, the electrons have to go somewhere. They don't just disappear. Now, you might seem like they disappear because maybe the electrons get pulled into the earth and they get what's called grounded. The earth acts as a giant electromagnet that can absorb charge. So, for example, wait till we get to the example actually, and I'll show you where the earth grounds it. But the earth can accept those charges, but they don't actually disappear. So if an object was negatively charged and then those charges flowed into the earth, it's not like the charges are being lost. They're just moving from one to the other. Okay, they're moving. Let's take a look at this idea of quantized charges. Here's an experiment that I'm going to go through in a minute. I'll give you a little video of it so you can see. That was done by this scientist, I think it was Robert, but his last name was Millikan for sure. And it's called the oil drop experiment. And what he did was, he recognized that if he bombarded oil drops with electrical charge, that he could get them to float. And what would happen to do this was, he would have what's called a diffuser. Like you ever spray like perfume? That's what a diffuser is. It's also called an ionizer. So it takes oil. Imagine spraying oil through a perfume thing. It would be all like a mist of oil. So they're literally oil droplets. The oil droplets would fall into this container, and the container was charged. They were charged plates. So the oil droplets would be falling through, then electrons would bombard them and attach the oil droplets, making them negatively charged. Then if they're negatively charged, then you make the bottom plate positive or negatively charged also. What would happen is it would repel, it would push back up. So the oil droplets would start to float. What he recognized was that every oil drop that floated had a charge that was a multiple of this number. And it was really interesting to see. So for example, there was an oil droplet, right? There was an oil droplet that had, let's say, for example, 2 electrons on it. As a result, what he recognized was that the charge on this was negative 3.2 times 10 to the negative 19 coulombs. When an oil droplet had 3 electrons on it, it was higher up, right? So this was like a negative plate. I should draw a plate the other way, actually. Hold on. This was like a negative plate on the bottom, and this was a positive plate on the top. So gravity's pulling down, so these droplets want to fall, but the negative plate is repelling this, so it's pushing it back up. So if there were more negative charges on something, for example here with 3 negative charges, it would be more negatively charged, so it would repel even more. So it was higher up. An oil droplet with just 1 negative charge would be a little bit lower. But they were all spaced out. And they were spaced out at specific heights. And what he noticed was that the charge on this one was negative 1.6 times 10 to the negative 19. This one was negative 4.8 times 10 to the negative 19. So as a result, what was he able to conclude, do you think? If he recognized when there was 1 electron, that was the charge. When it was 2 electrons, that was the charge. When it was 3 electrons, that was the charge. So what could he conclude as a result of this?
Like the more electrons, the smaller the number. Like the number of
Well, you're looking at the negative sign. That's what you're saying. Decreases, but forget the negative sign for a second.
Okay.
More electrons mean this number here gets... Yeah, so like 1 electron was 1.6 times negative because it's a negative charge. Ignore this negative if it's confusing you. So this is the charge on an electron. Well, 2 electrons was this. 3 electrons was this. So we say that charge is quantized. Quantized. What does quanta mean?
Make it bigger.
You're right, but more specific.
It's how many, isn't it how many?
Yeah, how many? So specifically how many? So like it goes up by a specific amount of how many it is. It does go up, yes, but specifically, notice these are multiples. Double 1.6, you get 3.2. Triple 1.6, you get 4.8. So what we recognized from this experiment was really pretty cool. The idea that charges all come as a multiple of the elementary charge, which is what E is at the top here. The elementary charge is a function of whether it's positive or negative, if it's a proton or an electron. If it's a proton, the charge is 1.6 times 10 to the negative 19 coulombs. Coulombs are named after scientists, by the way. We'll go into more coulombs with the next sections. But the unit of charge is called a coulomb. If it was an electron, it would be negative 1.6 times 10 to the negative 19. So this is the general charge for a proton, right? This is the general charge for a proton or an electron. Just know to put a negative sign right here if it's an electron. So let me show you a quick video of this.
Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron.
By the way, in 1909, this guy was only like 22 years old. Very smart.
He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall.
Gravity.
When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them.
See how they stopped
By
at different heights?
adjusting the applied voltage
All the ones
and
with more
observing
charge
the
stopped
droplets
here.
both with voltage off and voltage on,
So some
Milton
stopped
was
here.
able to determine that the charges on the droplets were all multiples of the smallest value, 1.6 times 10 to the minus 19 coulombs. He took this to be the charge on a single electron.
So if the
In
object
1909, Robert Millikan
if the object stopped or the oil droplet stopped higher up, it meant there were more charges on it because it repelled that negative plate and moved higher. So he saw literally groupings. There were groupings of oil droplets here. There were some here. There were some here. And he was able to see that those were increments of 1.6 times 10 to the negative 19 as an actual charge. So why is this important? The idea behind this is that if we're looking at charged particles, you physically cannot have something like 1.7 times 10 to the negative 19. Why not? Why couldn't you have 1.7 times 10 to the negative 19? It's not a multiple of 1.6. What are the multiples of 1.6? 3.2, 4.8, 6.4, 8.0, 9.6. Okay, so only multiples of 1.6 were allowed or are recognizable. You physically can't have like an electron and then a piece of an electron and as a result have this at like negative 1.9. Okay? So the idea was that he came up with the concept that the electrical charge on an electron or proton is called the fundamental charge. And everything occurs in multiples of this. Even electricity that flows. When electricity in the circuit is flowing, it's the electrons that are physically moving. Now, there are millions upon millions of electrons flowing in that circuit. So as a result, you have a much larger amount of charge that's passing. And as a result, you have what's called voltage. And we'll talk more about that in chapter 18 when we get to that. Okay, so let's go to the next slide. So we're going to talk about two types of materials, insulators and conductors, of which you know what they are, I think. Give me an example of something that would be an insulator that's not listed on here, obviously. But something that you would use as an insulator.
Fiberglass is used as an insulator.
Fiberglass, now that's an insulator for thermal insulation. Yes, I should specify. Electrical insulators. You're right, thermal insulation, like piping, stuff that's around pipes to keep hot water hot, that's thermal insulation, different than insulators for electrical. An insulator in electrical, right, does not transfer charge easily. So what's an example? Yes, rubber, glass, plastic, but what's an example physically we've seen?
Like the core.
Yeah, very good. The insulation, insulator, insulation. Insulation on a wire. So let's take a look. Here, you've got a simple wire, right? On the outside of this wire, you've got this rubber coating, the insulation. Now, what if, for example, you needed to expose some of the ends of these wires? So right now, there's metal copper wire in here, but the insulator's on the outside. So if there was an electrical current flowing through here, and I held this, nothing's going to happen to me. I'm not going to get electrocuted, especially if it's not a large amount of voltage, too. So if it's just a battery hooked up, you can get a little zap, but nothing bad. Now, here, this is a wire stripper. Have you ever heard the term before, wire stripper? So it's got a bunch of different little circles on it. They look like teeth. And the circles up here that you're seeing, you could use for different gauge wire or different diameter of insulation. So this wire, if I use this bigger one here, it's not going to be able to allow me to strip it off. But if I use one of these upper ones, and go to like right maybe here, okay? I'll wiggle this around here a tiny bit. So I'm cutting through the wire, but I'm not cutting through the copper. And I can pull off the end, and now what do you see? You see all the wire underneath it. So all you literally did was strip the wire. So now you've got all these copper filaments coming out of here. The copper could be twisted, it could be attached to another area, and then you could join the circuit. So the idea is that this metal on the inside, this copper, is a conductor. Most metals are conductors. It allows electricity to flow easily. The insulator, for example, this rubber, is an insulator where it does not allow charge to transfer easily.
I was just going to ask about going back.
Yes. Man, it's like the third person today. You're not the first person, believe it or not. All right, I'll wipe the tissues are right there if you want to grab one on the way. So, here's my. So the other thing we're going to talk about for a second are semiconductors. Semiconductor. Now, a semiconductor is traditionally an insulator, but it's an insulator that has been infused with specific metallic atoms. For example, if you took an insulator like rubber and you infused it with silicon, you would get a semiconductor. So something that is normally an insulator but acts as a conductor because of the fact that it has metallic atoms in it. That's what a semiconductor really is. And then there's another term called the superconductor. Anybody ever hear the term superconductor before? A superconductor is a conductor when cooled down to a low enough temperature exhibits what?
It's like magnet. It's like charged almost. I know there's like an example where like there's a magnet and you show something with like a nitrogen.
And you can see it floating and stuff. Yeah, the same idea is what you're saying. A little bit different because that has to do with friction, but the same idea is exactly there. When electrons flow through a circuit, they get resisted by the circuit. So the metal, although it can move them, there is still some resistance in metal. So electrons are flowing, right? It's like, imagine water flowing through a pipe. Water flows through a pipe, but doesn't the pipe wall slow it down a little bit? Isn't there some friction between the water and the wall? You might not recognize how much friction there is, but there is some friction. Now, if you make the pipe a little bit narrower, there's more friction and it builds up pressure, and we talk about it. Well, with electrons, they flow through the metal, but the metal does resist the flow a little bit. But a superconductor, you take the metal and you cool it to a low enough temperature, and it acts as a perfect conductor. There's literally, or not literally, but there's, what's the word? There's negligible, that's the word I'm looking for, there's negligible resistance in a superconductor. You cool it down to a low enough temperature, and the circuit continues to flow with almost no resistance whatsoever. That's what a superconductor is.
Negligible circuit.
Say again?
Negligible circuit. What you said, negligible.
Negligible resistance in the circuit. Negligible resistance. Because normally, even if something is a good conductor, it still has some resistive nature to it. It still wants to resist the flow of the electrons because of like traffic. Think about electrons flowing through a pipe or through a copper wire. It's like traffic. They're going to bombard. But if that's cooled down to a low enough temperature, the atoms that would slow it down in the metal are stopped. They don't move anymore. So it causes it to be able to flow easily through it. So it's negligible resistance. A negligible resistance in a superconductor. All right, let's take a look now at three methods. All right, three methods of charging. First, charging by contact. Charging by contact. An example of charging by contact would be that balloon in your hair. All right, for example, take your hair or take the balloon, rub it against your hair. You're creating some sort of abrasive resistance between your hair and the balloon, causing the electrons to move from one insulator to the other. Let me think for a second. If you use something that's an insulator and you charge it by rubbing against the surface, the charge will remain on the balloon. So you rub the balloon on your hair, you remove it from your hair. Your hair falls back down, it's okay, right? And if you take that balloon and put it against the wall, it might stick to the wall because the balloon is still charged because it's an insulator. It doesn't want to let the flow into the wall now because it's an insulator. If you did this with a conductor and you charge it by contact, what a conductor wants to do is it wants to come back to equilibrium. So if you take a piece of metal and you charge it by conduction, by touching it, it'll have a negative net charge. But then if you take that object and move it and touch it to something else, the charge will flow right out of it automatically. Because it's a conductor and it wants to get back to a net state of equilibrium. The same positive and negative charges. Whereas an insulator, take that balloon after it's been charged, put it on the wall, the charge is not going to flow into the wall and become a neutral charge. The balloon will remain charged while it's on the wall.
How do like certain walls have like a whatever, like or sticks to it, and then others like don't really?
I mean, it has to do with whether or not they're charged, but I don't know what's the
Like this, like stalls in the bathroom for some reason, like will like literally just like take your hair and like put it
Really?
on the wall. Like yeah, sometimes you see like your hair on the wall and it will like stick there. And, like that's disgusting, and your hair will just kind of like.
And the doors are made of metal, right? Is it plastic or is it metal?
Really?
Isn't it?
But it's painted, right?
Yeah.
It could be the paint itself. Now, usually, spray paint is charged. Why do you think spray paint might be charged? Yeah. Spray paint is naturally charged, so when you spray it on the metal surface, it literally pulls toward the metal. So, for example, when you spray paint a car in like an auto industry, so it's going through the assembly line, the spray paint is negatively charged. They induce a positive charge on the metal, so literally there is no spray paint that's left anywhere else. It all gets pulled onto the actual car. So the paint might be the charge that is there. It's possible. I don't know. It's a good question, but it probably is. And also, if you've been like brushing your hair or doing anything with your hair or moving your hair could have a charge to it. So it sticks to the wall like the balloon did the same way. Your hair is an insulator. It's not a conductor. So it will remain charged if you charge it some point earlier, and it might stick to the wall as a result. All right, so that's charging by contact. That's the first method. Let's go to the second method. The second method is what I'm going to try to demo for you tomorrow. I'm going to try to demo all these for you tomorrow if I can. And I have a charge meter, and you can see the actual amount of the charge. So the second method is called induction. And with induction, here's what's happening. You start with an object. This is all conductors, though. The object is conductor, okay? You start with the conductor here. Now, you bring it near another conductor that is negatively or positively charged. So the one in the middle here is neutral. It's got positive and negative. You take like a metal rod. You take a wool cloth, rub a wool cloth on it. It'll charge it one way or the other. I forget which way it charges it. I think it charges negatively. So you bring that negatively charged object near a neutral object, what happens? All the electrons in this neutral object, they don't want to be near these electrons. What do they want to do? They want to move away, don't they? Because the same charges repel, as Seagrex told us 2 seconds ago. The negative. What? Sorry, Kat. I had to call that one in. So the negative charges move over here because the rod is all negatively charged. It wants to move the other way. Now, when you hook up a wire to that, though, what's going to happen? When you hook up a wire, the wire is a conductor. This is a conductor. This conductor wants to be neutral. It wants to be evenly charged. But right now, it feels like it's negative because of this. So all these electrons are going to flow through this wire into the earth. That's called grounding. You're grounding this now. So now, since all these electrons flow out, what's left only? What's left if the electrons on the right side flow out of this? Only positive charge. So in part C now we see that when we remove this wire, when we detach the wire from the conductor after the electrons flowed out into the ground, into the earth, we're left with a sphere with only positive charge. And now we can remove this rod of whatever it's made of, metal. You can remove this metal rod from the actual proximity of the sphere, it's not touching, and you're left with a sphere with only positive charge. So the idea behind induction, again, is that you're using two conductors, you're bringing one conductor that's charged near the other one that's neutral, causing the neutral one to separate in charge, like a dipole, like in the hydrogen bonds in chemistry. So you have the negative, or in this case the positive over here, the negative over here. You hook up a wire, all those negatives flow out the wire into the ground, you then remove the wire, and you're left with only positive charge. You remove this rod, and you're left with a sphere that's been charged by induction. Only positively charged. Now, if you walked up to this, and you touched it though, what would happen is, electrons would flow out of you into it, and you get a little zap. So if you touch a sphere that's positively charged, you're going to get zapped. Because the electrons from you want to flow into it, causing it to be neutral. Okay? So when you get that like static electric charge, you like touch something, you get a little zap, that's what's happening. It's an imbalance of charge. It wants to get to a state of electrical equilibrium, really, like force equilibrium. Yeah.
If it was only negative, that's possible, we could have that too. Is it possible to have it only be negative?
Yeah, and then they would jump off of here onto you.
So it's still gonna be that.
Yeah, it'd be the opposite way though. The electrons would flow one way or the other.
In the actual definition, it says, you put them next to each other in the diagram, and it says they're touching.
They're not touching, yeah. Write a note down. They're not touching. It's just very close. Very close. Saw another hand somewhere.
Seabrook.
Yeah, I was just wondering, like, why you were talking about like Zach and stuff and like shocking,
Mm-hmm.
but what happens if like two people, you know, like is that like,
When they, like, if you like touch somebody over, you get a little zap from them.
Is that like one person has to be positive and the other one has to be negative?
Or one's neutral and the other's charged in some fashion or other. Usually, that happens when your rubber shoes create static electricity with like a carpet. Ever rub your feet on like a carpet and then like touch somebody and you zap them? Because when you're doing that, you're creating a net charge on your body. So you're inducing a charge by contact on your body actually that way. And then when you touch somebody by contact, that charge that you induce on yourself is going to them. The flow of that charge is the zap you're feeling. By charging it on yourself, you don't feel it. You're not like, it's not like you're feeling like, oh geez, this hurts or something. It doesn't happen. When you touch somebody, the imbalance there, you can literally see a little electrical charge. You can try it sometime if you want to. You do it at home, get your like brother or sister, zap them. Go take socks, rub your socks for a while on the carpet. Okay? And then have them like enter the room on the carpet and then touch them. And if you look close, you'll see a little zap go between the two of you. That's the electrons flowing from one to the other. Let's go to the last thing now. The third method. So we have charging by contact. Right? Charging by contact, which could be with insulators or conductors. Then we had charging by induction, which was only with conductors. And now we have charging by polarization, which is with an insulator. Now, an insulator, its charge does not easily flow. So instead of separating, right, so watch. You bring a charged object near an insulator now. Instead of the charges literally separating and being negative here and positive on this side, the atoms realign themselves and orient themselves as a dipole. And they're still together, they're not separate. Like in the last one, the sphere showed positive on this side and negative on this side. It's still neutral, it's not changing, they're not separating, they're just reorienting themselves. Okay, so when you use polarization, what you do is you bring a charged object near an insulator, causing the insulator to realign its molecules. Now, as a result, if you get close enough to it, it'll actually draw the paper toward the actual object, and it will stick. This positive and this negative will cause that to stick to one another, and that's the example you're seeing here with the comb and paper. Rub a comb through your hair, bring it to paper, and you'll see it. Okay, you'll literally see it pick it up. What's happening though is polarization in this case. There's no contact needed for this to happen, but you can have contact afterward when the two things are charged. If you want, for a little bonus, okay, if you could demonstrate some sort of static electricity, electrical charge, with a balloon, with something, but demonstrate it and make it work so that it actually works. Okay, and you can pick whatever you want to do. I'm not going to specify what kind of thing. You can use a balloon, a comb, something else. You can do the one I was telling you with carpet, but some sort of video of this, whether it be charging by contact, it'll probably be charging by contact because, or polarization, but you're probably not going to do it by charging by induction because you have to ground with a wire and stuff, which we haven't even gotten into how to physically do that. Okay, but if you want to do a video of charging by contact or insulation, or insulation with polarization with insulators, you can do that as well.
But like, you know, like those projects where you like take a paper clip and then you like magnetize it, would that be
Different.
That's different?
Yeah, we'll get to that though, Kat. We'll get to that when we do, when we look at magnetism and electrical circuits. We're going to see how they create a magnetic field around them and stuff. And one of the science club projects is actually doing that this year. So hopefully when they're done, we'll be able to use that in class to demonstrate what's happening. No? Discussion? Okay. Any questions besides that? So this is all what? Not mathematical, but really conceptual. Okay, so expect this on your test tomorrow, on Thursday rather. Okay, for conceptual parts for this. The homework for this is not due tomorrow, obviously. Problem sets are due tomorrow. This homework's due Thursday, lab is due Friday for you guys. Okay?